All right, let's jump right into this explainer, where we're going to rigorously audit clinical study designs. And by the end of this, I'm going to save you from what I like to call the ultimate mathematical testing trap. You know, if you've ever looked at a medical study and felt a little dizzy trying to figure out exactly how the researchers put it all together, and more importantly, if their math is actually legal, well, you're in exactly the right place. So grab your metaphorical briefcase because today we're acting as clinical lawyers.
Here's our docket for today's audit. Number 1, the timeline matrix. Number 2, the snapshot vector. Number 3, we'll do a quick design identification drill. And finally, number 4, the fatal math trap. Let's get to it.
Section 1, the timeline matrix, focusing on exposure versus outcome initial vectors. To start our cross-examination, we've got to look at the laws of motion in research. Whenever you review a protocol, you're faced with a 50-50 dilemma. It's all about the tipping point of the assembly vector. The judge demands an absolute audit of the starting point here. Did the investigator group people based on what they were exposed to, or because they already had the disease? If you start with exposure, meaning you group people into those who were exposed to a risk factor and those who weren't, you're looking at a cohort study. But if you start by grouping people by their outcome, say, finding cases who already have the disease and matching them with controls who don't, you are looking at a case control study. This initial starting point literally dictates absolutely everything that follows. Think about the timeline directionality for a second. Cohort studies always track forward from an exposure. A prospective cohort follows patients forward in real time into the future, say towards the year 2030. A retrospective cohort, though, uses historical records from the past, maybe from the year 2010, identifies the exposure back then, and then tracks the patients forward through their charts to a later date. Case control studies, on the flip side, always anchor in the present day with an outcome, and they look backward in time to probe for historical exposures. Now, as clinical lawyers, we have to filter out the noise. And let me tell you, the calendar year that data was collected, pure noise. People get tripped up all the time thinking retrospective automatically means case control. It absolutely does not. The calendar year is totally irrelevant. We have to solely audit the starting signal. Did the researchers group people by exposure first or outcome first? Once you master that, you'll never mix up these two moving timelines again. Okay, moving to section 2, the snapshot vector. Let's talk about prevalence and temporal ambiguity. So, what happens when we abruptly stop the clock and shift from a moving timeline to a stationary cross-section? Well, in a cross-sectional study, there is no forward tracking. There's no backward probing. Instead, we take a single, simultaneous snapshot. We sample a population and assess both their exposure and their disease at the exact same moment, completely ignoring the timeline. This design measures prevalence, which is the proportion of people who have the condition right now, rather than incidence, which is about new cases developing over time. If you're sifting through the evidence and you see high signal indicators like massive electronic surveys, mailed questionnaires, or data pulled from routine physical exams done on a population at a single point in time, you are almost certainly looking at a cross-sectional design. They're actually incredibly efficient for figuring out just how common something is at this very moment in time. But here's the catch, and this is a huge takeaway. Because everything is measured simultaneously, the fatal flaw of the cross-sectional design is temporal ambiguity. It cannot definitively prove that the exposure happened before the outcome. I mean, it can show you that two things are correlated for sure, but because you only took a single snapshot, you really have no idea which one came first. We've all heard the phrase correlation is not causation, right? Well, the cross-sectional snapshot is exactly why that rule exists.
All right, section 3, the design identification drill. Time for some clinical vignettes.
Let's put you on the witness stand and test your skills. Get your detective hat on for scenario A. Investigators want to know if a new anesthetic agent causes hypothermia. They pull surgical logs from 2018 to 2022. They identify 500 patients who got the new gas and 500 who got the standard gas. Then they review the charts to see how many of them developed hypothermia. So what's the design? If you said retrospective cohort, you nailed it. Why? Because the initial assembly vector was based entirely on exposure status, literally which gas they received. Even though all these events happened in the past, the investigators started with the exposure and tracked the patients forward through the historical charts to look for the outcome. Okay, let's try scenario B. To evaluate the link between a specific pesticide and Parkinson's disease, researchers recruit 150 patients from a neurology clinic who have Parkinson's and 150 age-matched healthy controls. They then interview both groups about their past agricultural employment.
What do you think the design is here?
The verdict on this one is case control. This is your classic setup. The study strictly started with the outcome status. The patients were selected precisely because they either had Parkinson's or they didn't. Only after that initial grouping did the investigators look backward in time, probing the subject's history for the pesticide exposure. Finally, scenario C. Researchers send out a massive electronic survey to 5,000 nurses asking just two things. Do you currently take a daily multivitamin, and do you currently have a diagnosis of hypertension? What's the design? Yep, it's a cross-sectional study. It's perfectly characterized by that simultaneous snapshot assessment of both the vitamin use, which is the exposure, and the blood pressure, the outcome. There's no tracking forward, no looking backward, just a single slice of time. And now for our final act. Section 4, the fatal math trap, or what I call the executional pearl. Here is where the judge brings down the gavel on the most catastrophic execution gap you'll see in study biostatistics. Case control studies group patients by outcome status, right? Because of this, their appropriate mathematical measure is exclusively the odds ratio. They are great for establishing an association, but because of how they're built, their mathematical toolbox is strictly limited. You absolutely cannot calculate incidence or relative risk from a case control study. Seriously, think about why for a second. The investigator artificially decided exactly how many cases and how many controls to enroll. If I randomly decide to recruit 100 people with a super rare disease and 100 healthy controls, boom, my study suddenly has a 50% disease rate. That apparent incidence is totally artificial. You can't determine true incidence, which means you cannot calculate true relative risk. Cohorts get relative risk, case controls get the odds ratio. Period. So I'm leaving you with this non-negotiable law of biostatistics. Always audit your starting vector. The very next time you see a flashy medical headline claiming a massive risk based on a backward-looking survey, pause and ask yourself, did they use the lawful math, or did they fall right into the ultimate statistical trap? Court is adjourned. Thanks for hanging out for this explainer, and stay curious.